Newton's second law, remember, is F equals ma. F equals ma. That's the sum, the vector sum of all the forces. It's equal to the acceleration times the mass of the body that those forces are acting on. And so you will need to use Newton's second law, just basically this concept, that the sum of the forces is equal to the mass times the acceleration, for problems that include forces acting on an accelerating body. So last video we talked about problems that for which the body was not accelerating. There's constant acceleration at least. But for problems that require Newton's second law, that just means that the body is accelerating, right? So that just means that the procedure is basically the same, except for when you do the sum of the forces in the x. Before, we were cataloging those forces and we were setting them equal to 0 just by default, right? Because the body was at rest or it was at constant velocity, therefore no acceleration. But now, Newton's second law, you will catalog the forces just the same, but you'll set it equal to mass times acceleration in the x at least. And then same thing for the y, right? So it's virtually identical here, except it's actually accelerating. And so you have to consider that. It's actually accelerating. And it's usually advantageous to choose axes where the acceleration is along one of the axes, so that you can say acceleration is 0 in one of the axes, say y, and it's something positive or something in the x direction, right? So then you could just have one acceleration, so you don't have to have components of acceleration. But we're going to go based off those same 5 steps that we identified before, right? So step 1 was identify target variables. I won't even write it. Step 1, identify target variables. Step 2, we're going to sketch the situation, label the relevant variables and their values. Remember, keep it simplistic. 3 is to do your free body diagrams. You might need more than one. Oftentimes you do. And you're going to choose your axes that make your life easier. So along the direction of acceleration or along the direction of the majority of your force vectors. Make your axes work for you. 4, you're going to get your equations. This is the really only difference here. So you're going to get your equations, but you're going to set at least one of them equal to ma instead of 0, because it's going to be accelerating in one way or the other. Or rather, if it is accelerating in one direction or the other, you need to remember to say that it is accelerating instead of writing 0. That's really the big difference. And then additionally, we didn't come across any problems in the last video using Newton's first law that needed the constant acceleration equations, although they may apply, right? Because acceleration can be 0, and that's constant. It's more often the case that they apply here. You'll run into more problems where you need your constant acceleration equations, right? So there's 4 of them. So go back to your notes or go back to the textbook and recall what those 4 were. Remember, each of them pertained to missing something. So like one was missing x and one was missing an acceleration. I don't remember the order that we listed them on, but you should have some notes near you when you're doing these problems that list off those equations so you can just kind of reference them quickly. And then you solve. Once you have all your equations, you solve. So we're going to do a couple examples just like before, just like last video. We're going to do a couple examples with Newton's second law. And you can see they're largely the same, except you have to include the ma part, right? So the acceleration is not 0. So I'll put up here, let's see, here's the first one we're going to do. It involves an ice boat. I didn't know what an ice boat was before this, but this problem involves an ice boat. Is that about straight for you guys? Somewhat. Oops. All right. So this is their sketch for the ice boat, in case you were curious. It's like a nice spring day in a very cold place. Okay, so I'll give you a chance to read that over. So there's a force, wind, that's blowing this thing, right? And it's a constantly applied force. And so it's accelerating in this direction. So the acceleration is going to be in this direction. So we need Newton's second law. It's not traveling at constant velocity. There's a constant force, but if you constantly apply a force, you're going to, and there's no opposing force or anything, then you're going to have an acceleration in that direction. So what does Fw, the force of wind, exert on the ice boat? So we are solving for that force, Fw. So step one, we're looking for Fw, which is not the weight, but the force of the wind. All right, so two, our sketch, you might be satisfied with that. I usually prefer to draw my own simplified sketch. So there's the ground, the ice, right? So ice is intended to just say it's frictionless. We haven't covered friction, that's the next video. So it's frictionless. Here's our ice boat. It has some mass, perhaps. Yes, the mass of the ice boat and the rider is 200 kilograms. So I'm going to say m equals 200 kilograms. Right on there. All right. And then there's an acceleration in this direction. That's just to remind myself, we're using Newton's second law here. There is an acceleration. Alrighty. What are some other things we know that we could just attach to the sketch, just to write down things that we've identified? Well, let's look at this second sentence. A wind is blowing along the direction of the runners, so that caused our acceleration. So that 4 seconds after the ice boat is released, it is moving at 6 meters per second. So 4 seconds after the ice boat is released, that means it started at a stop, right? So that means that its position at time equals 0 is we can call that 0. But it's going to have a velocity. So velocity is 6.0 meters per second. And that's when t is equal to 4.0 seconds, right? That's what all that stuff translates to. It's telling you that it starts at a stop. So v naught is equal to 0, right? Starts at a stop. That's what I meant to do, is v naught, not x naught, but x naught we can call 0 anyhow. And then after 4 seconds, the velocity at time equals 4 seconds is going to be 6 meters per second. So they've given us the information, we expect to have to use it later. So that's a first clue that we'll be using our kinematic equations, or our constant acceleration equations. Okay, so step 3, I'll go ahead and switch gears here. I'm talking about ice, so might as well use an icy color. Step 3 is to do our free body diagram. So it shouldn't be too difficult. We're ignoring friction. It has some weight, so I'll do mg because it gives us our mass, so we'll just write it in terms of mg. It has some normal force because it's contacting a surface here, so we have n. And we have the force of wind pushing it this way, and I'm imagining, since it's accelerating, this is kind of a large force. Maybe that's a little exaggerated, maybe not. But this is our force, capital W, of the wind. So everything's at 90-degree angles, and so it makes sense to do nothing other than call this our x, and this our y. Right? That If you want, you can relabel the mass here, just to remind yourself, and if you want, you can say that it's accelerating. We can do that if we want, so like acceleration is this way, and we can call mass something, right? And you can say it's equal to whatever, and if we had any fancy angles of things going on, then we'd label our angles now on the free body diagram, but we don't. So we don't even have to worry about component vectors at all. So this is our free body diagram completed. And so now, let's go ahead and go back to this guy. Now, for step 4, this is where we are finding our equations. So for, we're going to do the sum of the forces in the x, and the sum of the forces in the y. And we only have one body. So kind of a simpler problem compared to if there were two bodies happening, right? We don't care about the ground, that's not a body, the wind isn't a body. It's just the boat. So the sum of the forces in the x, well there's only one force in the x, so Fw, it's a capital W, and there is acceleration in that x direction, right? So it just so happened that we labeled our axes following both guideline rules, right? So most of our vector forces lined up this way, so our axes were placed this way, it's most convenient, but also the acceleration is directly along one axis, so that's awesome. So that way we could just say is equal to ma. We don't have to say max because it's not a component. I suppose you could say that max, the component of acceleration along the x-axis, is equal to the total acceleration, right? Convince yourself that that's true, but I'll just skip right to it and say that the total acceleration is along the x-axis, so this is the total acceleration here. So now y, we have our normal force minus mg, and the ice boat is not crashing through the ice, hopefully yet, and it's also not flying up into the air, so there's no acceleration up or down. Remember, it's just the same thing. All the acceleration is in the x direction. So kind of in the y component, you can think of Newton's first law applying, and the x component, Newton's second law applies. So they're all working in tandem. Basically, you're just adding tools to your toolbox, and you need to know when to use each one. Okay, so we have this. What were we solving for? We were solving for the horizontal force Fw. How much does it exert on the ice boat? Well, I guess we have an expression for it right here, right? And we have its mass, but what is its acceleration? We're not quite done yet. We can't express it in terms of the acceleration. It gives us enough information to find the acceleration so that that's just a number, right? So what constant horizontal force, Fw, does the wind exert on the ice boat? So at this point, we might be able to see that this doesn't really get us anywhere. It was good to catalog it. It doesn't get us anywhere. This equation is really what we're concerned with, but what we're after now is this acceleration. We want to find the acceleration, and we have our other equations to help us, our constant acceleration equations to help us. So alongside 4, we're still getting more equations. We're finding out which equations we need. I'm going to rewrite the quantities that we have. We have v naught, we have v, and we have t. And I suppose we also have x naught, if we call x naught 0, usually a given. So these are the quantities that we have. So look at your constant acceleration. And then we want to find acceleration. So go ahead and look at your constant acceleration equations. Go back in your notes and find them. There should be 4. And find which equation might work if we have these things to find A. See which one might be the most appropriate. So when I look, I see an equation that goes like v equal to v naught, right? And we probably labeled them with x, the x doesn't matter, right? That's just along a certain direction, along a linear direction. So I'm going to exclude the x. It could just as likely be y, right? We could use it that way, just along a straight path. So v is equal to v naught plus a t. And so it just so happens that we are talking in the x direction, but I'm going to write it more generally like this so that you understand that it could be applied in other directions as well. So do we have everything here? We have v, yeah, we have v naught, we have t, and we're searching for a, so we can solve that. So that looks to be our equation. So now, I'll go ahead and keep working in pink. But we are on to step 5 now. We have all the equations we need, and we'll solve. So I'm going to take this one here, and I'm going to solve it symbolically first for a, and then I'm going to plug the a into this equation up here, and then we can plug everything in, right? So we have a being equal to v minus v naught divided by t. Did I do that right? Check for yourself. All right, so then you take that and you plug it into Fw is equal to m times what we just got, v minus v naught divided by t. If you went back and checked when I said I made a mistake on that first example in the video previous, I went back and looked and I did not make a mistake. I just, in my notes, skipped a step, and I thought maybe I had made a mistake. So if you're searching and searching and you didn't find a mistake, then put your mind at ease. I was correct. All right, so now we have everything. We can go ahead and plug this in. I'll let you do that, and you should get 300 newtons. That's the force of the wind. So we were able to solve that because we had the concept of Newton's first law, Newton's second law, and we had our constant acceleration equations. So we were able to pull this equation out and solve it. So we're just pulling tools that we need out of our toolbox to get to the target variable. All right. Go ahead and slide this up. We'll do another example here. So I'll throw it up here, let you read it while I'm setting everything up. It's pretty short, pretty simple, huh? Sometimes that can be deceiving. Is that relatively straight for you? All right, and I believe they give us a diagram. There we go. It's pretty simple. Could simplify it a tiny bit, but not too much, I would say. You think you could solve this on your own? Pretty much the same process, but now we have some sort of a slope going on. But if we're comfortable with our components, right, finding components of vectors, assigning axes conveniently for us, if we're comfortable knowing which way the acceleration is and using F equals ma instead of F equals 0, in other words, Newton's second law applying, and when Newton's first law applies instead, then we can probably get this. So a toboggan loaded with students, total weight W, slides down a snow-covered slope. The hill slopes at a constant angle A, or alpha rather, and the toboggan is so well waxed that there's virtually no friction because, of course, we have not covered yet it. What is acceleration? What is its acceleration? So right off the bat, step 1, what are we solving for? Acceleration. We want to know its acceleration. Done. Nice. All right, let's do this. It's snow covered, so I'll use white to draw our simple diagram. In this case, I probably would not draw a simplified diagram. It's pretty simple, but I'll go ahead and do it anyhow because it doesn't take too long. So this is alpha, and this is our toboggan, and it has some weight, right? Some weight. That's how they give it to us, and they're not giving us any numerics. So they're wanting us to solve for its acceleration symbolically. So we're not going to get any numbers, but we will find the answer all the way down to just before you would ordinarily plug in numbers. Arguably more useful, yeah? It's more general, you can apply it to more things. Alright, and this, you can say this is a solid surface if you want. We're ignoring friction. Okay, so step 3. Step 3, we're going to draw a free body diagram. So what's going on here? So we have our toboggan. It has some weight. We'll do this since it gives it to us in terms of weight. And it has a normal force, which is normal to the surface that it's sliding on. Right? Normal. And that is at some angle. Right? So we'll think about that in a second. Is there any more forces? It's well waxed, so there's no friction. Are there any more forces? I see no other forces. We're not considering wind, there's nothing pushing it. It's just going down the hill because of gravity, right? So acceleration will be in, let's do this. Acceleration is going to be in this direction, right? So there is acceleration happening in this direction, generally. So it's probably smart to choose our axes along that direction. And so, in fact, that is what I will do. So I'm going to say that this, being 90 degrees there, that's going to be our positive x direction, because that's the direction of the acceleration. You know it's going to be going downhill that way. It's not going to go through the surface of the hill, right? And so then we'll say this is our y, positive y direction. That work out okay? So based on our first guideline of choose your axes in the direction of the most force vectors that align with those axes, we could go with either. There's no preference based on that general rule of thumb, right? We could align our axes so that weight lines up with the axes, or with the normal force lines up with our axes. But if we go, if we add that additional guideline of put your axes along the lines of acceleration and it helps you out, then it collapses the decision for us, and we see that it is preferential to put it in terms in line with the normal force because the acceleration is in that direction. So this is just making our life easier. You could certainly choose the axes the other way. You just have to consider components of both and then deal with finding the total magnitude of acceleration by squaring the two components and then square rooting that, right? Adding them and then square rooting. But anyhow, so we've chosen our axes. We've drawn our free body diagram. We can find the component of weight here, right? And this axis negative goes back that way. So I'll pick a new thing here. Wow, that's pretty hot. How about that? So this is the amount of the weight vector that is in the negative y direction, and this is the amount of the weight vector that's in the positive x direction. So we want to find what the magnitudes of each of these component vectors are. So we have to start thinking about our angles. So what is alpha? Where is alpha? Alpha, if this is our hill, right? This is alpha. Alpha. That's alpha. And so this would be like 1 minus alpha, right? Or in other words, this, right? Or not 1 minus. This would be like 90 minus alpha, and so this would be alpha, since this is a 90-degree angle here. So this is alpha, and it might be best to just go off of that and think of it that way. All right, so now we can find our component magnitudes, right? So this one is going to be weight times either sine or cosine, right? Well, it's adjacent to there, so it's going to be cosine alpha, right? And this one, this would be alpha then, right? And so it's going to be opposite. So this is going to be weight sine alpha. Every time you do it, you get a little bit faster and a little bit more comfortable with that kind of thing, finding the component vectors. Okay, so now we're on to step 4. I'll stay with green here. Step 4, find our equations. So sum of the forces in the x, and that is the x direction that we have defined, right? So the sum of the forces in the x. That means that we have this guy here and nothing else, because the normal is in the y, and the other component of the weight is in the y as well. So w for weight sine alpha, and that is equal to some acceleration. It is accelerating in the x direction, and it's the full acceleration. It's not the x component of acceleration, or it is, but it's equal to the full acceleration, because there's no y component of acceleration. It's not accelerating in the y component, or the y direction that we have chosen. It's only accelerating in the x. So that's how we've made our life easier there. And then sum of the forces in the y, and we may not even need this part of it, so we could skip this if we already recognize at this point that this gets us where we want, right? But just to be completionist, we have normal minus w cosine alpha, and that's equal to 0. See, that doesn't involve acceleration at all, and so we don't really care about it because we're trying to solve for acceleration. So if you recognize that before writing it out, then you maybe didn't have to write it out. If you wrote it out and then recognized it, it's fine. It's not a waste of time because you're learning. Okay, so we have this expression here, right? And so we want to solve for acceleration in the direction of, or rather, in terms of its weight, right? It doesn't give us mass, I don't think. So, well, I suppose if weight is m times g, whatever the m is, and we have an m there, then maybe it is worth writing a different way. I'll go to gold. This is when we start solving. So I'm just going to rewrite it. mg sine alpha is equal to ma. And the only reason I wrote it that way is because I noticed we have m's on both sides that could cancel. And so if we're solving for alpha, that's equal to g sine alpha. I mean, we're looking for acceleration. I don't know what I said. If we're looking for acceleration, then it's equal to g sine alpha. And we're done. We're done. Can you imagine if we had not chosen our axes carefully? It would have taken a little bit more, because we would have had acceleration, components of acceleration along both. We would have had to involve a lot more stuff. We would have had to find the total magnitude of the acceleration, and there would have just been a lot more going on. But because we cleverly chose our axes, we're done already. All right, so before we do more problems, I want to introduce friction and talk about the different types of friction. So that'll be the next video. And then that will open us up to a lot of the common forces that you'll see, and you can do virtually any problem involving Newton's 3 laws. And it's actually a really fun part of the class. It feels empowering to be able to solve these types of problems. So talk about friction next, and then we'll wrap up with some dynamic circular motion, I think. Dynamics of circular motion. See you next video.